So another look that you get when you are measuring fluid flow in a pipe is the idea of fully developed. Okay, fully developed is an expression that we all say a bunch, and what we mean by that is before I stuck my hot wire anemometer right here, and I maybe, let's say, created a velocity profile. Fully developed means downstream of the pipe, I did the exact same thing. So this is going to be, let's say, at a z naught. So x. This would be an x naught, and this would be like an x1 downstream of the pipe. So one other thing is, like, after a while of flowing down the pipe, if it was laminar especially, I could do the experiment here, and I would make a plot of a velocity profile. And then on downstream, I would do the same experiment, and I would get the exact same velocity profile. So fully developed is an expression that, that the velocity profile is not a function of the axial direction of flow. After some amount of time, it seems like this was the same profile, whether it was at x naught or at x1. So mathematically, if this is going to be a u, right, I like to think of it as just like fully, you have u is a function of r. It changes with r, but that's it, right? So fully developed, is a way of saying that it's a function of r. It's not a function of x. So if I'm at x naught and then x1, this is not a function I'm looking for based on my differential equations. Fully developed means that this doesn't change based on x. But that's sort of problematic because this is just a long straight pipe, and I've always sort of drawn a section of pipe with these little cutoff ends. But in reality, fluid has to get to a pipe, right? It has to be pumped from a pump or just from a reservoir, even like in that Reynolds experiment. So in reality, what happens is there is some part of this when the thing is changing. So if I have some reservoir like this, okay, that's a free surface of the fluid. This has a density. If I was right here, if I was right here, it almost looks like a plug flow at first. It just kind of looks like a bunch of arrows that are the exact same. And as it moves down, it kind of smooths out, and then it goes kind of perfectly smooth, right? So you could kind of do the exact same, where now this is going to be x equals 0. This is maybe some intermediate x. And then it kind of at some point, now what happens is these are exactly the same. So there is a point, though, in all real systems, the applied part, where there's some entrance length when it comes to getting fluid into a pipe, where I cannot say that the velocity is independent of x, right? So that's this process of changing the velocity distribution, right? Every point of this little profile right here, right? Each one of these profiles gives you a velocity. So that distribution, how do I plot? It really looks like a little bullet head moving down the pipe. But you can just see, you could even put streams of dye in here, and you would see, it would look kind of straight. And if you did a bunch of separate pieces of dye, so like an array of dye, maybe like here that's spitting out dye, you would see how things would be changing if you measured particles and velocities. But you could do these measurements. You can see how there's a little section at the entrance of getting fluid to a pipe where things are changing. They're not fully developed. And fully developed makes a lot of equations a lot simpler and a lot more, analytical for us to calculate things. So you could then start doing measurements based on that pipe, and I'll draw those pictures next.